Okay, we're going to do one more physics drill today. That's going to be student questions. So I've got my list of topics here, and we're pretending that we got a student who's going to ask a random question about one of these topics. So let's see. He's confused about multiple expansion. We write the potential as the sum of the monopole and all the poles. We get the Legendre polynomials. I don't understand how we decide which terms actually matter for a given charge distribution. It's based on symmetry arguments. Do we have to explicitly compute all the multiple moments? How does that relate to the physical meaning of taking the far field limit? Which terms actually matter for a given charge distribution? Um, okay. Well, dang, this is kind of a difficult question. Usually you have to do a sum of all the terms at first. But if there's symmetry or antisymmetry, you can possibly select only even or odd L's. Now the far field limit means far to infinity leaves only the b over r term, so the ar term goes away. Now we have to absorb charge integral into b. And possible to convert. Okay, I think we're gonna stop there. I don't know if this is correct. Symmetry arguments. Far field limit. Yeah, so the RL solutions are discarded and the decaying branch remains, which is why we get this. Net charge does not equal zero. The leading term selection. If charge does not equal zero, then the monopole dominates. That makes sense because if you're going out to the R's, the high R's, you know, R squared is going to fall faster than R, so that makes sense. Absorbing the charge integral. Yes. Okay. Next question. Normal modes for coupled oscillators. When we write the equations in matrix form, the mass matrix N, stiffness matrix K, I don't get why solving that automatically gives the allowed frequencies. What is the actual physical meaning of turning the differential equations into this eigenvalue problem? Why do the eigenvectors correspond to specific motion patterns rather than just being algebraic artifacts? This question is insane. Alright, well, I mean, you you have, say, a system with two modes, for example, or sorry, two oscillators, for example, you're going to expect two modes since there's two equations of motion. Now, the equations can be put into a matrix form so that it can be solved in one go, a system of equations rather than one by elimination. Um, the determinant sets sets up the characteristic equation, so the roots can be solved. We get two modes. The eigenvectors, um, what is the point of the eigenvectors? Just scale the percent terms, I guess. I don't know. I don't know what the eigenvectors do. So, um, so we do the matrix form to solve the linear equation system simultaneously. We get our little characteristic equation. For non-trivial amplitude, the determinant must vanish. Roots are the loud frequencies. Yeah, this is not right. Yeah, it fixes the relative amplitudes and phases. It scales the amplitudes. So the eigenvectors scale the amplitudes of how much each uh, um, frequency affects each oscillator. Yeah, they scale the amplitudes of how much each frequency affects the oscillator. Because each oscillator here, like the cosine, that's an oscillator. It's gonna have the eigenvector scaling it. Okay, next question. These are crazy questions. Method of images for conductors. When we replace the conductor with fictitious charges to enforce V equals 0 on the boundary, how can we be sure the resulting field is physically valid everywhere outside the conductor? Are we guaranteed uniqueness just from the matching boundary conditions? Um, Matching Dirichlet boundary conditions is what guarantees uniqueness. Uh, it's due to to uh, trying to take the voltage difference of 2 points or two different values between two different, assumingly different values, and taking a derivative somehow. to reveal that it's not the same voltage at both values. We get a difference of like a voltage difference, and we used Green's identity. Surface term vanishes because U equals 0 on the boundary, leaving that equals 0. Since the integrand is non-negative, I think this part right here, U equals 0 on the boundary. Okay, I guess if U equals 0 on the boundary, we do, we would just get this equals 0. Um, yeah, this is kind of a weird proof. It doesn't really make a lot of sense. It's kind of hard to visualize this, you know? So, yeah, it's hard to visualize that equation there. All right, let's try one more question. I'm confused about separation of variables. Right V, introduce separation constants. How do we know those constants must take on discrete values that lead specifically to the Legendre polynomials and spherical harmonics? Those constants must take on discrete values rather than allowing continuous spectrum of solutions. Quantizing angular functions? Oh my lord. How are we gonna answer this question? How do we know that those constants must take on discrete values that lead specifically to Legendre polynomials and spherical harmonics, rather than allowing a continuous spectrum of solutions? Well, um, when we separate the equations, we tend to get something like A plus B plus C equals 0. Um, we, well, it starts more like R double prime over R plus theta double theta over theta plus V double prime over V equals 0, which can be treated like A plus B plus C equals 0 because um, each coordinate must work that system, meaning each equation is independent of the coordinates. Therefore, they are all constants. Their coordinates. Therefore, they are all constants. But the discrete values, though, because see, this is where they're talking about these constants here have to take on discrete values. I think we have to use boundary conditions to enforce well, this allows solving sort of three differential equations: radial, polar, azimuth, which ends up in the Cauchy-Euler uh, spherical harmonic and simple harmonic solutions. I think we have to enforce the potentials specific points, which could possibly include either V naught, implying L equals 0, or cosine, implying L equals 1, or cosine squared, implying L equals 2, etc. Okay, I think that's the answer. But yeah, why do the constants become discrete? I don't know, rather than just constants. Okay, so you're saying that azimuthal symmetry of 2 pi leaves only integer n's. That makes sense. And then uh, Legendre tries to diverge at the poles, and this is separation constant satisfies. Oh, yeah, yeah, the Legendre poles at 0 and pi would diverge if we divided by sine theta. So that's why we have to use cosine solutions. I guess, or maybe, I guess it's only reason, the only thing we have to do is use L plus 1, and then the radial, and yeah, the the solutions must also um, avoid divergences at the origin and infinity. So the generic solutions diverge. Look, because we're dividing by sine of theta all the time here. So if you try to divide by, sine of 0 or sine of pi, the solution diverges. And the solutions that remain are the ones that are a function of cosine. Those that exist. I'm not sure why we have to do this. Yeah, this is probably the hardest question that we were asked, because why on earth would we be forced to use these discrete L plus 1 things? It's a little confusing. The other boundary conditions make a lot of sense, like this one at 0 and infinity. So yeah, so that was a pretty tough drill. Those are the student questions that we had today. Oh wow, hey, how's it going, Tony? The lens maker formula. Yeah, the lens maker formula is good. Yeah, that's a good formula. In fact, there's something really important about the lens maker formula. So let's go ahead and take a look at that. It's in optics. Sorry about the late reply. Well, actually, one of my favorite formulas to use is something that has to do with that. It may not be the lens maker itself, but here it is. It's 1 over f equals dO plus 1 over di. 1 over f equals 1 over dO plus 1 over di. It's the lens maker. You can also set that equal to two different like lenses, like the n of a lens minus the n of like a medium, and multiply that by the curvature radius of curvatures here. But what's really important is if you're using multiple lenses, and this is actually like the best formula ever. I'm pretty sure Galileo invented this formula, but that's just a hunch I have. Because the only way to put multiple lenses together, and you have like say there's like 15 or 20 lenses that you're going to put together. If you really wanted to like try to solve for that system, um, well, this is a really important equation to use, is that the object for the second lens is a ghost object. It's not a real object. So DO2 ghost is equal to the distance between the two lenses minus the distance of the first image. So taking the distance of two lenses, subtracting the distance of the first image, gives you the distance of the object from the second lens, or the ghost object. This equation here makes all the lens equations really, really easy for multiple lenses. But anyway, that's pretty much related to the lens maker. It's right next to it. Hopefully this answers the question about the lens maker formula. Thanks for showing up, and you'll have an awesome night.